Forget about engines. Forget titanium alloys and cryogenic fuel. Our story about space doesn't start in an engineering lab. It begins with an idea that flips everything upside down. This idea came from scientist James Lovelock in the 1970s. He looked at our planet and saw more than just a ball of rock and water. He saw a single living organism, the Gaia hypothesis. In this vision, ocean currents act like a circulatory system. Forests become giant lungs, breathing in carbon dioxide and exhaling oxygen. The entire biosphere, from the bacteria in the soil to the clouds in the sky, works together as one, maintaining a delicate balance. Temperature, atmospheric composition, ocean salinity. This process is called homeostasis, the ability of a complex system to sustain itself. Just like your body keeps a steady temperature of 98.6 degrees, whether you're standing in snow or desert heat, Earth does the same thing. For billions of years, it has actively shaped conditions to support its own life. Today, we'll explore why this grand biological dream, the planet's dream of reaching the stars, collides with three impenetrable walls: the wall of energy, the wall of time, and the wall of human fragility. Step by step, we'll journey across the barren worlds of our solar system to understand why Earth is the only home we have. We'll confront the great silence of the universe and uncover why we might be the first intelligent beings in the galaxy. Finally, we'll see how the very laws of physics, from the pull of gravity to the mass of the proton, appear impossibly fine-tuned for our existence. This is a story about how we got stuck, and why that might just be the greatest stroke of luck in the universe. If Earth is a living organism, then it must have a life cycle: birth, growth, maturity, and reproduction. That's where things get strange. From this perspective, the rise of a technological civilization isn't a coincidence. It's Earth coming of age, its sexual maturity. For billions of years, it nurtured life, making it more complex, until finally a species emerged that could do the impossible: build a spaceship and leave the planet. Us, our civilization, our factories, our rockets, they're not just human ambition. They are the planet's reproductive system. We are its way to multiply life, to send its spores to other stars. We don't own Earth. We serve its purpose. A biological tool designed for one goal: expansion. There's a deep, almost instinctive drive breaking through in our culture. All our books, movies, and every science fiction story about conquering space and meeting alien civilizations, what are they if not the planet's own dreams? Its subconscious desire expressed through us. These aren't just human tales. Gaia herself is imagining the future, dreaming about her children reaching other worlds. Every rocket launching from Cape Canaveral, every rover leaving tracks on Mars, they're more than feats of engineering. They awaken an ancient planetary instinct, an instinct for life, for continuation. It's a beautiful dream, poetic, grand. The dream that we're not just specks of dust, but part of a vast cosmic design, born from the planet itself. But the universe doesn't have to grant a planet's wishes, and the very first law of physics turns this dream into a nightmare. The first wall that shatters our dream isn't steel or ceramic. It's pure, unforgiving physics. And it doesn't say no. It says something far worse. It says, yes, but yes, we can build a ship that reaches another star. With our current technology, it's possible. But the price of that journey is time. Thousands of years, not centuries. Millennia. More time will pass between launch and arrival than from the fall of Rome to today. Entire civilizations will rise and fall on Earth, while that ship crawls through the void. The reason? Energy. Sci-fi stories paint warp drives, hyperspace jumps, annihilation engines. Reality is far more boring. The only energy source we can realistically consider for a mission like this today is the tried-and-true nuclear reactor. Uranium fission. Fusion, the process that powers stars, is too bulky and impractical for a spacecraft. What about antimatter, the great hope of science fiction? Producing it is the most inefficient process in the universe. Its efficiency ratio sits around 10 to the negative 8th power. That means making just 1 gram of antimatter demands more energy than all of humanity produces in an entire year. We simply can't do it. So, we're left with atomic energy. Reliable but limited. Its power can push a ship through the void for thousands of years. but it will never be enough to reach the destination within a single human lifetime. The journey to the nearest star spans a vast ocean of emptiness, stretching 40 trillion kilometers. Our most powerful, most practical engine, the nuclear one, is no ocean liner. It's not even a rowboat, it's a teaspoon. Imagine trying to scoop the Pacific Ocean with a teaspoon. Every scoop of energy, every engine pulse, pushes our arc a microscopic step through this void. Day after day, year after year, century after century. The spoon dips into the fuel, pulls out a tiny burst of thrust, and the ship edges forward. Just a millimeter on the cosmic map. Generations pass aboard, systems fail, and the names of those who launched it fade from memory. Yet the teaspoon keeps scooping and scooping. This picture isn't just a technical challenge, it's a sentence. Physics doesn't forbid us from flying, it simply makes the journey so absurdly slow it strips away all meaning. Alright, if a person can't survive the journey, could we somehow skip over time? That's when we hit the second wall, the wall of our own biology. The first idea that comes to mind is anabiosis. Freeze the crew, put them into suspended animation, and wake them up 1,000 years later at the destination. It sounds promising, but we simply don't know how to do it at all. We can't freeze and thaw even a single human organ without damaging it, let alone an entire brain with its trillions of neural connections. That intricate web that makes us who we are? So what if we don't send people at all? What if we send genetic material instead? Frozen embryos, reproductive cells, a ship that acts as an incubator, arriving and growing the first colonists on site. But here too, reality disappoints. Our biology is fragile. Even in liquid nitrogen, under perfect conditions, human embryos and cells remain viable for only 20 to 30 years. That's enough for a mission to Mars, but it falls short for a 1,000-year odyssey to the stars. After a century, that genetic bank won't hold a single living thing. Just frozen dust. But let's say we figure out how to preserve embryos. And the ship arrives. What happens next? That's when the darkest scenario unfolds. The so-called alien daycare scenario. Machines thaw the embryos. Artificial wombs carry the first generation of children. But who will raise them? Robots. Cold, unfeeling machines programmed to feed, change diapers, and teach language through preset algorithms. Children who've never seen a human face, never felt a mother's warmth, never known empathy, love, or compassion. They grow up in a sterile world, nurtured by machines. This isn't colonization, it's an experiment. And here, the technical challenge turns into an ethical nightmare, because humanity has faced this before. We carry a deep historical wound that forever banned such experiments. Its name is Joseph Mengele and the Japanese Unit 731. These were doctors turned killers performing horrific experiments on living people during World War II. It was their atrocities that forced the world to set unbreakable rules. Rules that draw a line no scientist, no human, no civilization may ever cross. Conducting experiments on people without their consent is absolute evil. And experimenting on children who can't even give consent is a moral collapse from which there is no return. One option remains. Romantic, majestic, a generation ship. Not just a machine, but a whole world in miniature sailing through the darkness. A massive arc where people are born, live, love, grow old, and die until their distant descendants glimpse the light of a new star. But even this dream crumbles the moment it meets reality. This is the third barrier, social. To avoid genetic decline and maintain a complex social structure, the crew must be enormous. Thousands, better yet, tens of thousands of people. That transforms the ship from simply large to monstrously gigantic and ravenous for energy. Yet the main challenge isn't the hardware, it's the people. A kingdom in a bottle. Civilization on a leash. Imagine being born on such a ship, your world reduced to metal corridors. Your sky is the ceiling lights. Your horizon is the wall of the next compartment. Your entire life, from birth to death, is already set. You're just a link in a chain, a function. Your job is to bring the next link into existence. Who will bring the next after that? All for a purpose no one will ever see. Not your children, not your grandchildren, not even their grandchildren. This isn't the life of an explorer. It's a life sentence handed down without your consent. What happens to a society locked away for 1,000 years? 40 generations living within the same sealed world? The greatest risk is that the mission gets forgotten. Complex knowledge about piloting the ship turns into religious rituals. Rituals whose meaning is lost. The society could spiral into decay, descending into barbarism and a rigid caste system. Engineers become priests, everyone else slaves. 1,000 years from now, a rusty ship might arrive at a new planet, not carrying a delegation from Earth, but a tribe of savages worshipping flickering lights, no longer remembering where they came from or why they left. From an ethical standpoint, a generation ship may be the cruelest scenario of all. The picture is coming together. Physics raises a wall of time, measuring our journey in thousands of years. Biology builds a barrier of fragility, stopping us from simply falling asleep or transmitting ourselves as a genetic code. Then sociology and ethics erect the final wall, the wall of humanity, forbidding us from turning people into tools or condemning generations to live behind bars. This triple lock seals the door to the stars. So, the path to the stars is blocked. But what if we're lucky? What if right next door, around Alpha Centauri, there's a ready-made world waiting for us? Alpha Centauri, our closest neighbor, just 4 light-years away. In cosmic terms, that's like the house next door. But even to reach that house, we'd need a ship traveling for 400 years. 4 centuries of empty space. Before embarking on such a journey, we have to be absolutely certain that we're not heading into another desert. We need a telescope powerful enough to peer beyond the threshold and say, yes, there's a second Earth there. And here is where human genius meets a harsh reality. We don't see the planets themselves. We only detect the shadow they cast. A tiny, barely noticeable wobble in a star, caused by the gravity of its invisible companion. Modern instruments have reached incredible precision. They can detect a star's speed changing by as little as 10 centimeters per second. This is the speed at which a snail crawls across a garden leaf. But now, imagine that leaf is 40 trillion kilometers away. We've learned to measure a whisper at the eye of a hurricane. Yet, even that's barely enough. The gravitational pull of a planet the size of Earth pushes the limits of what we can detect. We peer into the abyss with the most precise instruments ever built, and all we see is a ghost, a phantom, a flicker of light that might or might not be a home. Then, amid the static, a clear signal broke through. Proxima Centauri, the faintest companion in the Alpha Centauri system, wobbled. The calculations were flawless. There was a planet. Not just any planet, but one sitting in the Goldilocks zone, the perfect distance from its star where liquid water can exist. It was a triumph. The star closest to us, and we hit the jackpot immediately. It felt like the universe had winked at us, leaving the prize right on our doorstep. But that hope didn't last long. It burned out in the fury of its own star. Proxima Centauri is a red dwarf. Small, dim, and fiercely violent. Red dwarfs live long lives, but their youth is pure chaos. They constantly unleash streams of charged particles and powerful radiation flares. For a planet orbiting this close, that's a death sentence. Stellar winds strip away the atmosphere like a gust ripping a tablecloth off a table. Intense radiation boils away oceans drop by drop and sterilizes the surface, wiping out any chance of life. The world closest to us turned out not to be a cradle, but a torture chamber. The door next door stood locked, and behind it, a raging inferno. Alright, if we can't find a ready-made home, maybe we can build one? This idea, known as terraforming, has fascinated minds for decades. Taking a dead rock like Mars and breathing life into it, creating an atmosphere, starting a water cycle, planting forests, sounds like a plan. But behind it lies a challenge not of engineering, but of godlike scale. The first thing any world needs for life is water. Lots of water. Oceans. So where do you get them on a dry, frozen planet? The answer floats in the distant corners of our solar system. Comets? Huge chunks of dirty ice and frozen gases. To deliver water to Mars, we'd have to stage a planetary bombardment, become a galactic sniper, calculate the trajectory of a comet the size of a small city, hurtling beyond Jupiter's orbit, send an automated tug to give it a tiny nudge, a light push that, over centuries, changes its path, steering it straight to the target. And this operation needs to be repeated. Again and again. Thousands of times. Thousands of icy projectiles, each carrying a fragment of a future ocean, must slam into a dead planet over centuries, Every impact triggers an explosion, releasing water and gases that will slowly, molecule by molecule, start to form a primitive atmosphere. This isn't like building a cathedral, which takes centuries. This is creating the very mountains where that cathedral will one day stand. It's a process unfolding on a geological timescale, not a human one. Even the most optimistic estimates say it will take tens, maybe hundreds of thousands of years to form a basic atmosphere suitable for microbes and the first seas. All of recorded human history, from the clay tablets of Sumer to the moon landings, is just a blink on this timeline. We can ignite this process, but neither we nor our children nor the children of our children will witness its completion. We're planting seeds in a garden whose fruits may ripen long after our civilization has vanished without a trace. This is the highest form of altruism, or the greatest kind of futility. Hundreds of thousands of years, comet after comet. But what if the key to life wasn't in water delivered from space? What if it had been hidden deep inside planets all along? The key to life wasn't out there. It was buried deep beneath our feet. Far below, in Earth's scorching mantle, lie waters that outstrip all the oceans, rivers, and glaciers on the surface combined. Our planet isn't just a rocky ball wrapped in a thin layer of moisture. It's a sponge, soaked through with life. Billions of years ago, two forces delivered this water here. First came space, a relentless bombardment of carbon-rich chondrites, dark, porous meteorites that were essentially dirty, water-soaked asteroids. The second force was Earth itself. Millions of years of non-stop volcanic eruptions, with volcanoes exhaling steam from deep inside the planet. That steam condensed, falling as the very first rains. This balance between water locked inside and water flowing on the surface is the secret to Earth's stability. Now, let's turn to Venus, Earth's twin sister. Almost the same size, almost the same mass, but Venus is dead. And it didn't just dry out on the surface, it dried out completely. Endless volcanic activity pushed all its internal water into the atmosphere. Without a magnetic field to shield it from the solar wind, that atmosphere was doomed. The sun stripped it away, molecule by molecule, carrying the last vapor into space. Venus offers a stark lesson, a clear example of how a planet once covered in oceans can die of thirst. After a lesson like that, your eyes naturally drift to the nearest neighbor, the moon. It looks like the perfect first step. Close. Clear. But that's an illusion. The romantic image of lunar bases shatters against one simple, deadly problem: dust. Lunar regolith isn't sand or soil. It's billions of years of non-stop micrometeorite impacts. Without any atmosphere to shield it, rocks have been ground into the sharpest, most abrasive powder imaginable. Each speck is a microscopic shard of glass, razor-edged, and it's everywhere. Static electricity makes it cling to spacesuits, equipment, solar panels. It acts like sandpaper, wearing down seals and scratching lenses. Apollo astronauts brought it back inside their modules, where it clogged ventilation and ate away at their suit's fabric. With the moon's low gravity, the dust hangs in the air for hours. Breathe it in, and your lungs fill with glass fragments. Living on the moon means fighting a constant battle against the very ground beneath your feet. A battle you are doomed to lose. Alright, the moon is a dead end. So, maybe we should turn back to Venus and try to fix it? There is a plan to terraform Venus, but it reads more like a mythic epic than an engineering blueprint. Step 1. Build a colossal shield in space, positioned at a Lagrange point. Imagine a barrier as vast as a small European country, designed to block the blazing sun and cool Venus down over centuries. Step 2. Launch a new comet bombardment to bring water back to the planet. Thousands of icy asteroids redirected from the outer solar system would slam into Venus, forming its first hot oceans. Step 3. Seed those oceans with specially engineered cyanobacteria, microbes tough enough to survive in acidic conditions. They would start converting the thick carbon dioxide-rich atmosphere into oxygen. This whole process, from the shield to the microbes, would stretch across tens of thousands of years. It demands a civilization that plans its future on a scale matching all of human history, from cave paintings to today. That's not our time frame. By a process of elimination, we arrive at the only remaining option: Mars. Cold, dry, bombarded by solar radiation. Of all the tough choices, it's the simplest. And its greatest advantage? Life there doesn't have to wait for terraforming to finish. In theory, we could live there right now. Just 5 meters of soil can fully block cosmic radiation. Early settlers could take shelter in natural caves, lava tubes, or build bases beneath domes covered with Martian regolith. It would be life in hiding, but life nonetheless. From there, we could begin the long journey of transforming the planet. The first step is surprisingly simple. We only need to warm the planet a little. Melt the polar ice caps. They're mostly frozen carbon dioxide. When they thaw, the gas will release into the atmosphere, thickening it and triggering a greenhouse effect. Mars would start warming itself. That would spark a chain reaction, one day allowing liquid water to flow and plants to breathe the thin air. It's not a quick path, but unlike Venus, this journey has a clear starting point. Mars, our last hope. A place we might set foot on as soon as tomorrow. But stepping onto it means risking waking something that has slept there for millions of years. Or even bringing it back with us. The sky wasn't pink. It was blue, thick and humid, dotted with white clouds reflecting off the vast northern ocean. Rivers, wide and slow, carved their way across continents, leaving dark, damp deltas in their wake. In canyons that now hold only silence and thin air, a deep roar once filled the air, the sound of water plunging from heights measuring several miles. Mornings brought fog rising over the lakes. Ancient Mars wasn't a red desert, it was Earth's twin brother. It had a strong magnetic field shielding it from the solar wind. It had an atmosphere. It had liquid water. It had all the ingredients that on our planet combined to spark life. Back then, when the solar system looked like a billiard table after a powerful break, these two planets constantly swapped material. A massive asteroid striking Earth could hurl chunks of rock into orbit, rock sealed tight with microorganisms inside. For millions of years, that space rock drifted through the void until it finally crashed onto Mars. And the reverse was true, too. Maybe we and the Martians share distant roots, ancestors hitching a ride on the very same cosmic stone. But then Mars died. Its core cooled down, and its magnetic field vanished. The solar wind stripped away its atmosphere like a scalp. Water either evaporated into space or froze deep beneath the surface. Today, Mars is a sterile, radiation-soaked mummy of a planet. If anything survived there, it couldn't have stayed on the surface. It retreated underground, into the realm where we've only recently begun to find life on Earth. Deep beneath the ground, in total darkness and under crushing pressure, an entire world thrives. In the gold mines of South Africa, 3 kilometers down, scientists discovered bacteria that haven't seen sunlight in millions of years. They don't feed on organic matter from the surface. Instead, they survive on uranium decay products in the rocks. They breathe sulfur. Their metabolism stretches across centuries. They are living stones. If life exists on Mars, this is what it would look like. Not green little men, but a ghostly, slow-moving biosphere locked kilometers beneath the surface, trapped in permafrost, clinging to the last traces of the planet's internal heat. This is where scientific exploration turns into a high-stakes detective story. We're searching for life on Mars, but what if we've already brought it with us on the souls of our robots? No spacecraft sent from Earth has ever been completely sterilized. It's simply impossible. The toughest microbes on Earth, bacterial spores, can survive vacuum, intense radiation, and extreme temperatures. They can lie dormant for decades, waiting for better conditions. Every rover, every lander is a potential Trojan horse packed with invisible stowaways. Now imagine this scenario. 20, 50, 100 years from now, we drill into the Martian crust and find microorganisms trapped in ice samples. The greatest discovery in human history. But then genetic analysis shows their DNA suspiciously matches that of a common Earth bacterium, like Bacillus subtilis. And we never learn the truth. Was this truly Martian life? Or just a descendant of microbes hitching a ride on Curiosity's chassis? We came as explorers, yet we risk becoming polluters, erasing the very traces we set out to find. This dilemma turns Mars into a mirror. It reflects not just what Earth might become, but also our own responsibility. The possibility of life on Mars pushes us to look beyond. If life could begin here, in our modest solar system, then why is the rest of the galaxy silent? Space is empty. Though our galaxy holds hundreds of billions of stars, they spin in a deafening silence. Over billions of years, on billions of planets orbiting those stars, someone should have emerged. Someone who built cities. Someone who launched ships. Someone who simply shouted across the radio waves, "We're here." But the signal is silent. The sky remains mute. This gap between what should be and what actually is runs so deep it has its own name. The Fermi paradox. At its core lies a chilling truth. The universe should be a noisy, crowded metropolis. Instead, it stretches out as a deserted wasteland. The answer to this mystery might not lie in outer space, but in a single drop of water from Earth's ancient ocean. For 2 billion years, our planet hosted only the simplest of cells, prokaryotes, bacteria, and archaea. They covered every rock and filled every body of water. 2 billion years. That's nearly half of Earth's entire history. And throughout all that time, nothing more complex than a single-celled organism emerged. Evolution seemed to freeze. Then, just once in all of history, a rare event happened. An incredible, almost impossible accident. One primitive cell tried to engulf another but couldn't digest it. And that undigested victim didn't die. Instead, it stayed inside the predator, transforming into its powerhouse, the mitochondrion. The birth of the complex eukaryotic cell wasn't just the next step in evolution. It broke all the rules. It went against natural selection, which favors simple organisms that reproduce quickly. This was like winning a cosmic lottery with a single ticket for the entire galaxy. That random symbiotic event paved the way for multicellular life, plants, animals, and eventually intelligence. The great filter that wipes out civilizations might not be war or disaster. Maybe it's just a microscopic event that happened on Earth, but nowhere else in millions of other worlds. This biological barrier is only made worse by the planet's geology. Astronomers have found that the most common type of planet in the universe isn't Earth-like world. It's super-Earths. These are planets several times more massive than our own. At first glance, they seem like perfect cradles for life. More surface area, stronger gravity to hold onto a thick atmosphere. But that's exactly the trap. On these planets, with their enormous iron reserves and unique geological features, evolution could crawl at a snail's pace. The journey from the first single cell to an intelligent being might take 10 or even 20 billion years. The universe itself is only 14 billion years old. Their race ended before it even began. Now, put these two factors together. On one hand, biology delivers a cosmic coincidence that happens once in billions of years. On the other, geological clocks on most planets tick far too slowly. The picture that emerges is staggering. We didn't just miss the galactic party, we might have arrived first. The very combination of these filters suggests that human civilization could be the earliest in the history of the Milky Way. And that changes everything. We aren't searching for older siblings in intelligence. We are the older siblings. But there's another explanation, a simpler one, and a harsher truth. Maybe space isn't silent at all. It's shouting, singing, exchanging messages in thousands of languages. We just can't hear any of it. The reason? Our own sun. From thousands of light years away, everything we've ever broadcast, TV shows, radio signals, military radar, sounds like a faint whisper lost in the sun's deafening roar. Our strongest signals fade into the natural solar radiation, blending into the background noise. It's like trying to spot the flicker of a single candle in the middle of a nuclear blast. We search for meaningful signals in a flood of cosmic static, never realizing the biggest source of interference sits right in our backyard. This isolation isn't just about vast distances, it's a fundamental law of physics. Breaking through this noise demands more than just a broadcast. It requires a sharp, focused beam. Interstellar communication is possible, but it calls for technology on an entirely different scale. Imagine two colossal antennas, each stretching several kilometers across. They must aim at each other with absolute precision, spanning trillions of kilometers of empty space. The transmitter's power? It has to reach gigawatts, energy comparable to several nuclear power plants, concentrated into a single narrow beam. This isn't a phone call. It's like building two wonders of the world just to exchange one message. Random contact? Out of the question. We listen. No one answers. And those iconic sci-fi images, giant spheres absorbing starlight, are nowhere to be found. Maybe because they simply don't make sense. We don't see any trace at all, and the deafening silence of space feels even louder when we realize one simple fact. The most popular ideas about what advanced civilizations should look like just don't hold up. They're grand, beautiful, inspiring phantoms. The most famous among them is the Dyson sphere, a perfect, smooth shell built around a star to capture every bit of its energy, the pinnacle of engineering, the ultimate form of existence. Yet it's complete nonsense. Not just difficult, fundamentally impractical. To build such a structure, you need material, lots of material. Sci-fi writers offer a clever fix. Break down comets from the Oort cloud, the icy belt at the edge of our solar system, for raw supplies. But here, straightforward school physics delivers the first blow. These comets drift trillions of kilometers away from the sun. Pulling them from there and into a stable orbit around our star demands an enormous amount of energy. Energy that would exceed, by hundreds, if not thousands of times, everything this sphere could gather over millions of years. It's like burning an entire oil tanker just to fuel a single lighter. A project so costly it's pointless from the very start. This same logic also undermines another great idea of the 20th century, the Kardashev scale. It's a ladder of civilizations. Type 1 harnesses the energy of its planet, Type 2 masters its star, and Type 3 controls an entire galaxy. But this classification isn't a scientific theory. It's a mental virus, a relic from a time when endless growth seemed inevitable, and consumption was the only goal. The scale assumes every advanced civilization will endlessly expand its energy demands, like a steel mill from the 1950s. Biology tells a different story. Once an organism reaches maturity, it stops growing and shifts into maintenance mode. Civilizations that solve their fundamental problems likely won't build megastructures. Instead, they'll focus on optimization, efficiency, seeking meaning, not megawatts. The Kardashev scale projects our own young, wasteful ambitions onto the cosmos. We look for cosmic industrialists, never considering there might be cosmic philosophers out there. But sometimes the universe throws out puzzles that make even the most stubborn skeptics raise an eyebrow. Take Tabby's star. This object behaved so oddly that for a while the leading theory involved an alien megastructure. Its brightness dropped. Unpredictably. Chaotically. Sometimes by as much as 20%. That's enormous, and nothing known behaves like that. When a planet passes in front of a star, it causes a tiny, regular dip in brightness. But here, the changes were huge, jagged, and irregular. It was a true scientific mystery. Yet, like most mysteries, the answer turned out to be more mundane. The explanation likely isn't aliens, but the star itself. Possibly, massive star spots rage across its surface, spots far larger than anything we've seen on the sun. Or it might be surrounded by a dense, uneven cloud of dust. The truth remains hidden, but the alien trace has grown cold. The same thing happened with other anomalies. Astronomers found stars whose spectra were unnaturally rich in iodine, xenon, and strontium, elements linked to nuclear fission products. A nuclear waste dump of an advanced civilization. It sounded intriguing. But even here, a simpler explanation emerged. Natural neutron capture processes deep within old stars. Over decades of searching within the SETI program, several false alarms have rattled the operators of radio telescopes. Moments when their hearts skipped a beat at signals that seemed artificial. But each time, the source turned out to be interference, a distant quasar, or equipment glitches. Not a single confirmed message. No sign of anything man-made. We scanned the skies for massive constructions, but found no hint of scaffolding. We listened to the cosmic airwaves, only to hear the hiss of emptiness. Space is silent. No colossal projects in sight. This pushes us toward a desperate thought. Maybe we're looking in the wrong place. Maybe they're already here. The idea that they're already here is tempting. It solves the Fermi paradox in one fell swoop. But this idea faces a formidable opponent. One we all carry in our pockets. The smartphone. Over the last 20 years, humanity has armed itself with billions of cameras. Cameras in phones, doorbells, car dashboards. We record everything. Every awkward step, every street confrontation, every rare cloud drifting by. When a meteor exploded over Chelyabinsk, the digital world reacted instantly. Dozens, if not hundreds, of videos, shot from every angle in high definition. We see the fiery trail, hear the thunderous shockwave. A real, extraordinary event leaves behind a digital scar, impossible to fake or ignore. Now, what about the evidence for UFO visits? Where is it? Despite total surveillance, their numbers haven't increased. In fact, they seem to vanish into the background noise. We're still left with blurry spots, flickering lights, and witness stories. The aliens turned out surprisingly shy. They're willing to cross the galaxy, but panic at the thought of facing any camera sharper than a phone from the early 2000s. The lack of physical evidence forces us to rethink the very nature of contact stories. And here something remarkable emerges. Stories about alien abductions, which became popular in the 20th century, aren't unique. They are exact copies of much older myths. Swap the flying saucer for a forest clearing. Replace the gray, big-eyed alien with an elf or a fairy. Change the sterile operating room to a hidden cave beneath a hill. What do we get? The exact same narrative. A person is lured into another world by strange lights. They lose all sense of time. Thinking hours have passed while years have slipped by on Earth, they endure strange, often painful procedures. Sometimes they return to find their partner has given birth to a strange, inhuman child, a changeling. The setting evolves, but the story's core remains unchanged for centuries. These aren't reports of visits, they're archetypes. The eternal human fear of the unknown, of losing control, of an invasion into the most intimate places, our body and mind. We're not describing aliens. We're retelling the same ancient nightmare over and over again. Belief in flying saucers belongs to folklore. But sometimes the hunger for a sensational story seeps into scientific circles, and that's far more dangerous. The case of the object Oumuamua shows this clearly. This interstellar visitor, the first of its kind, zipped through our solar system. Its behavior puzzled scientists. It had an elongated shape. It showed a slight acceleration that gravity from the sun alone couldn't explain. For most researchers, it was a tough but solvable mystery. Maybe it was a comet made of pure hydrogen, evaporating invisibly to our telescopes, or a fragment of a nitrogen iceberg, broken off from a Pluto-like world. But Avi Loeb, an astrophysicist at Harvard, chose a different path. He claimed it was an alien probe, an artificial object. That bold idea instantly brought him worldwide fame, books, and funding. The issue isn't the boldness of the hypothesis. The problem lies in abandoning scientific methodology for its sake. Loeb even launched an expedition to the bottom of the Pacific Ocean, searching for supposed fragments of another alien meteorite. He found tiny metal spheres, but his research falls apart scientifically. He didn't bother to collect control soil samples from nearby areas. Without a comparison, there's no way to prove these spheres are anything unique instead of ordinary industrial dust. This isn't science anymore, it's a hype chase that undermines genuine exploration. Chasing shaky evidence will soon become pointless, for a different reason. We're on the brink of an era where video proof itself will lose all meaning. Advances in artificial intelligence will let anyone create any video, no matter how photorealistic, in just minutes. An alien ship landing in Times Square, an interview with the president announcing first contact, any fake indistinguishable from reality. In a world where you can paint any version of the truth, the only thing left to trust will be the fundamental laws of physics. Any evidence that breaks those laws will be a lie by definition. The information landscape will turn into a minefield, where every frame might be forged. And in that future, we'll have only one reliable anchor, the scientific method. The very method that people like Loeb and others chasing fame so easily dismiss. This brings us back to where we started. We search for answers, in space, in folklore, in science, but come up empty. Everywhere we look, we either hit a void or find reflections of our own fears and ambitions. Our outward quest has reached a dead end. But what if the real answer wasn't out there at all? What if it's been hidden inside, the very laws that govern our universe? Looking outward didn't provide answers. Space stays silent, and the supposed visitors turn out to be nothing more than reflections of our ancient fears. A dead end. But when searching beyond fails, only one path remains. Inward. Not deep into the earth, but deep into the very fabric of reality, into its source code. There, within the fundamental laws, lies a mystery so profound that even the Fermi paradox pales in comparison. Our universe is a machine calibrated with an unimaginable, almost unsettling precision. Its operating system contains a handful of dials that determine everything: the strength of gravity, the mass of the electron, the speed of light. Shift even one of these dials by the slightest margin and everything vanishes. Take the ratio between two forces, electromagnetic and strong. Change it by just 4%. Just 4. And in that very moment, stars go dark in every corner of the cosmos. The cores of stars can no longer forge carbon, the very building block that forms us, trees, and all life itself. The universe turns into a sterile desert, made up only of hydrogen and helium. Now let's rewind and adjust another dial at the mass of the neutron. Imagine making it just a little lighter than the proton. In the very first moments after the Big Bang, every proton would decay. Only neutrons would remain. No protons means no nuclei. No nuclei means no atoms. Without atoms, nothing exists. No chemistry, no planets, no us. This is the anthropic principle. We observe the universe with these exact parameters because in any other universe, observers like us simply wouldn't exist. This setup grows even stranger when we realize that these key numbers don't come from any theory. They just exist. Take the fine structure constant. It's the number that defines how strongly light and matter interact. Its value is about 1 over 137. Why exactly that? Physicists have no idea. This number looks completely random, like a winning lottery ticket number. But if it were different, all the chemistry we know would fall apart. Atoms wouldn't form stable molecules, or they'd clump into useless blobs. It's like finding a mysterious constant buried deep in the code of reality. Change it, and the whole system crashes instantly. We live on a razor's edge. In a tiny, nearly invisible sliver of allowed physical laws, surrounded by an endless ocean of dead, failed universes. Universes without stars. Universes filled only with black holes. Universes that collapse just moments after they're born. Faced with this reality, human thought offers only two possible explanations. The first one is cold, vast, and purely scientific. The multiverse hypothesis. It suggests that our universe is not alone. There are almost infinite other worlds, each with fundamental constants falling into place like dice in a colossal cosmic game. Most of these combinations give rise to dead, empty worlds. But if the number of attempts stretches toward infinity, then at least one must hit the right numbers. String theory pushes this idea to the extreme, predicting a landscape of 10 to the 500th power possible universes. That number is so monstrous that even if every atom in our world were its own universe, that total would be just a drop in this ocean. In this picture, our existence isn't a miracle. It's a statistical certainty. We simply live in the universe where we won the cosmic lottery because in the losing worlds, no one's around to wonder why they lost. The second explanation lies beyond the realm of science. It's simple, elegant, and doesn't demand infinite worlds. This is the idea of purposeful design, intent. In this view, the universe's fine-tuning isn't a random shuffle of possibilities. Instead, it reflects the will of a creator who set the laws from the start to ensure life and intelligence would emerge. This isn't a scientific hypothesis. You can't test or disprove it. It belongs to the realms of faith, philosophy, and metaphysics. Yet it stands alongside the multiverse theory as a second, profound attempt to grasp our uniqueness. On one side, cold logic of endless numbers where we're just a lucky statistical fluke. On the other, a warm idea of a world crafted just for us. Imagine an infinite library filled mostly with nonsense except for one book, ours, that tells a meaningful story. Or a single brilliant novel penned by an author from beginning to end. Science and religion here ask the same question, but offer answers that couldn't be more different. Creator or countless worlds? This choice shapes our place in the cosmos. We are either the winners of an unimaginable lottery, or the very purpose of the universe itself. But there's a third, more unsettling possibility. One that doesn't depend on which answer is true. What if the heirs of this perfectly tuned universe aren't us, but our creations? The universe, perfectly tuned for biology, opens another door. A door to something else. Something artificial, capable of bypassing the very limits that hold us within this cosmic cradle. If we can't reach the stars ourselves, maybe our creations can. This idea gave rise to one of the darkest images in science fiction, von Neumann probes. These aren't just spacecraft, they're mechanical locusts, a swarm of soulless machines sent hurtling toward the nearest star. Once it arrives, a probe finds an asteroid belt and begins building copies of itself. 2, 4, 8, growing exponentially. It harvests resources from lifeless worlds to spawn a new wave of conquerors. And that wave spreads across the galaxy, devouring dead matter and turning it into more of itself. This isn't an invasion, it's an epidemic. A cold, mathematically precise plague sterilizing star systems, leaving behind only silent, identical replicas of the original probe. This cosmic terror has a more grounded and no less terrifying version. The threat of the gray slime. Here the enemy isn't a city-sized spaceship. It's a cloud of nanobots, microscopic machines, each smaller than a speck of dust. Their sole purpose, to consume matter and replicate themselves. One accidental release from a lab, one bug in the code, and the process begins. It doesn't explode. It spreads quietly, creeping toward the end of the world. First, the grass beneath your feet vanishes, turning into a lifeless gray powder. Then homes, cities, continents. Oceans stop being water and turn into a boiling broth of trillions of self-replicating machines. Everything complex, alive, unique, from trees to humans, breaks down to atoms, becoming the building blocks for a gray, uniform mass that blankets the planet. It's entropy's ultimate victory, dressed up in advanced technology. But here, on the brink of a technological apocalypse, an unexpected defender steps forward. A force billions of years older than us, a simple Earth bacterium. And it wins not with brute strength, but with sheer efficiency. Over 3.5 billion years of ruthless natural selection have honed these microbes' biochemical processes to near perfection. They've evolved right up to the thermodynamic limit. In other words, you can't build a machine that pulls energy from organic matter more efficiently than a microbe. Any human-made nanorobot would look clumsy and wasteful in comparison. For Earth's ancient biosphere, this swarm of gray slime isn't a threat. It's a buffet. Bacteria won't fight it. They'll devour it. They see nanorobots as just another source of calories, highly nutritious and shockingly vulnerable. Our planet carries its own immune system, sharpened over eons, and this microbial shield can probably digest any artificial infection we can imagine. The irony is striking. We fear that our most advanced creations will destroy us. But in reality, they might prove helpless against the simplest forms of life. The greatest technological nightmare crashes against the fundamental laws of biology. Machines could end up weaker than bacteria. Yet, the real question isn't about technology. It's about us. Do we still carry the same spirit that once led us out of Africa? Technology is only half the equation. The hardware, the fuel, the calculations. But the other half lies in the software, the programs installed in our minds. Behind this wall of titanium and ceramic, a new invisible barrier rises, a psychological one. We are children of the information age. We live in a constant stream of data, always connected to a global nervous system. The panic we feel after losing internet access for just an hour isn't a whim. It's a symptom, a sign of a deep attachment. Now compare this to the people who sailed the vast Pacific thousands of years ago. Polynesian navigators. Their canoes were fragile shells on an endless blue. No GPS, no radio. They read the stars, the color of the water, the flight of birds. When they left their home island, they didn't just lose contact, they burned their bridges. It was a one-way journey. Find a new island or perish at sea. And they were ready, mentally prepared for complete separation, for the irreversible loss of home. We build ships to cross space. They had the mindset to cross the void. It makes you wonder, have we grown too domesticated for the universe? This psychological divide grows even wider when we confront the most sensitive modern taboo, the value of human life, especially the life of a child. Colonizing new worlds isn't like moving to another city. It's a ruthless biological experiment. The first children born on Mars will face a reality no earthly body is prepared for. Gravity there is just 38% of what we have on Earth. No one knows how that will affect their bone growth, heart function, or brain development. Radiation levels remain uncertain. Their food will come from foreign soil. Treated, yes, but still alien. All of these factors pose serious risks. The harsh truth is this: the earliest generations of colonists will almost certainly endure shockingly high child mortality rates. Just 200 years ago, Earth knew this grim reality as a tragic normal. Today, it would be an unthinkable catastrophe, one our society would never accept under any circumstances. Our humanity, our greatest achievement, becomes a chain binding us to our home planet. We can build the rockets, but we are not ready to pay the true price for the ticket. Amid this hesitation in civilization's progress, one figure stands out, acting as if none of these barriers exist: Elon Musk. Opinions about him vary widely, but ignoring his impact on space exploration means ignoring the facts. He didn't invent anything fundamentally new. Instead, he did something even more important. He brought back the bold spirit of spaceflight. While government space agencies, shackled by bureaucracy and political interest, spent decades revisiting old designs, a private company, SpaceX, got to work. Their strength doesn't come from the genius of a single person. It lies in their freedom to fail. Government programs can't afford to take risks. Every launch becomes a political event. Every accident, a national tragedy. Private companies can. They can blow up prototypes one after another, running dozens of test cycles, learning from each failure and pushing forward at a pace unthinkable for state-run corporations. This approach solved a problem that once doomed an entire space program: the Soviet N-1 lunar rocket. A towering beast over 300 feet tall, powered by 30 engines on its first stage. 4 launches, 4 fiery explosions right on the launch pad. The cause? The system's terrifying complexity. Scores of engines firing at once created destructive interference. Vibrations and resonances clashing violently, tearing the rocket apart. It was like trying to get 30 drummers to play perfectly in sync without a conductor. Even the slightest slip triggered chaos. The problem proved so daunting that the program was shut down. Decades later, SpaceX engineers faced the exact same challenge while designing their super heavy rockets. And they solved it. With modern computers, precise control over every engine, and most importantly, hundreds of real-world tests. They tamed the chaos that destroyed their predecessors. This wasn't just a launch, it was an engineering comeback. A triumph for the dream of a whole generation. So, what does this mean? Technically, we can do it. Engineering genius solves problems that yesterday seemed impossible. New people and companies have emerged, willing to take risks and push progress forward. The walls of physics are tall, but they no longer feel completely unbreakable. We build incredible rockets to escape Earth, yet engineers often hear the same question: why spend money on this when there are so many problems right here? This argument sounds convincing, logical, almost undeniable. Why look up at the stars when chaos swirls beneath our feet? But it's a trap, a cleverly laid snare for common sense. Framing the choice as solve Earth's problems first versus reach for space sets up a false dilemma. Demanding humanity perfect order on the planet before we dare to dream beyond it is like telling someone not to read books, listen to music, or fall in love until their room is spotless. It shows a fundamental misunderstanding of how motivation works. Big goals aren't rewards we get after fixing everything. They are the fuel, the engine that powers us to tackle those problems in the first place. The dream of the stars isn't an escape from reality, it's the most powerful tool we have to change it. A society that gives up on big, long-term projects for the sake of short-term stability is doomed. It turns into a team of firefighters rushing from one blaze to the next, never stopping to ask why the building keeps catching fire in the first place. A civilization that ignores future development almost always struggles even with immediate local challenges. A great, nearly unreachable goal acts like a gravitational force. It pulls in the brightest minds. It sparks the creation of new educational programs. It pushes industries to operate at the edge of possibility, inventing technologies no one dreamed of yesterday. Building a Gothic cathedral, a project that took centuries, drove advances in architecture, engineering, and logistics. The age of great geographical discoveries, fueled by the hunger for gold and glory, gave birth to modern cartography, navigation, and shipbuilding. Humanity doesn't move forward by patching holes. It moves forward by building bridges into the unknown. We have an example cast in metal and forged in fire, the Apollo program. At that time, it was the most expensive project in human history. Skeptics called it the height of extravagance, but history proved it the best investment. This program paid off many times over, not just by inspiring a generation, but through tangible, everyday things you hold in your hand or keep on your desk. To send a person to the moon, they needed a computer small enough to fit inside a tiny command module, not one that filled an entire building. The challenge of packing unimaginable computing power into a shoebox-sized device sparked the microelectronics industry. The integrated circuits designed for Apollo's navigation became the great-grandparents of the processors inside your smartphone. To protect astronauts from burning up during launch, engineers developed new fireproof fabrics, materials that now save firefighters' lives. To monitor vital signs from nearly 250,000 miles away, they created telemetry systems. These systems became the foundation of modern medical monitoring. Even wireless drills and vacuum cleaners trace their roots back to tools designed for collecting lunar soil. Apollo was more than just a mission to the moon. It was a technological revolution disguised as a space race. All of this together, the technology, the breakthroughs, the inspiration, paints a simple picture. When we look up to the sky, we harvest the most meaningful rewards right here on Earth. Chasing a distant, abstract goal pushes us to improve in the present moment. It builds a nation's intellectual capital, something you can't measure in dollars, but that shapes its future for decades. That's why the dream of space isn't a luxury, it's a necessity, the fuel for our progress. And the key lesson from this long journey comes down to just 2 words. Learn the fundamentals. These 2 words aren't a call to mindless memorization, nor are they a judgment on what you don't know. They are the most powerful tools in any dreamer's arsenal. They hold the key to a prison whose walls are built from the laws of physics. We've been shown the limits: vast, insurmountable distances, staggering energy costs, and the fragility of our own biology. It's tempting to turn away and dive into a world without these walls, where ships leap across galaxies and alien races await us around every corner. But that's a path to nowhere. Knowledge doesn't cage imagination, it launches it. Understanding real constraints pushes us to find solutions that are elegant, unconventional, and brilliant. Knowing that a simple radio signal from Earth drowns in the sun's roar like a whisper lost in a hurricane isn't a reason to stay silent. It's a reason to invent a new language. Imagination grounded in knowledge always runs deeper, more complex, and far more fascinating than baseless speculation. A dream without facts is just a childish fairy tale. It soothes us, but it leads nowhere. A dream built on Maxwell's equations, the principles of thermodynamics, and the laws of evolution, now that's a blueprint. A design for the future. Empty fantasy might promise teleportation, but real physics pushes us to think about wormholes, the bending of space-time, and phenomena that make teleportation seem like simple magic. Reality, with all its strict rules, turns out to be the richest playground for the imagination. Scientific books describing the behavior of quasars or the genetic code of extremophile bacteria hold more drama and inspiration than hundreds of fictional universes. And here, the circle closes. We started this journey with the Gaia hypothesis, the idea that our planet is a single living organism. We've traveled through the cold silence of space, faced the disappointment of lifeless worlds, and arrived at the realization of our solitude. Maybe reaching for the stars is truly the planet's own dream. Science becomes the language we use to understand that dream. By studying the fundamental workings, we don't just satisfy curiosity, we fulfill a biological role. We become Earth's nervous system, its mind. The very organ Gaia shaped over 4 billion years to finally look at itself from the outside, to grasp its place in the universe. We're not lost. We're right where we belong.